Hey guys, welcome back to another video. I'm Tarish and welcome to TNT Academy. And today I'm going to be talking about Atomic Theory Part 2 or Lecture 2. So let's start. So in today's video we're going to be talking about Bohr's atomic theory. So after discussing J.J. Thomson's theory and Rutherford's theory in the last video, we understood that there is something called a nucleus through Rutherford's gold-foiled experiment, right? There's going to be something in the middle, and that's called the nucleus, right? So we've got a nucleus here, and inside our nucleus, we know there are positively charged molecules or positively charged protons and neutrons which are neutral charge. We have protons and neutrons in the nucleus, right? But it wasn't really clearly defined or mentioned how electrons are going to be there and what the diagram could possibly be, because Rutherford never made a structure, right? So now this is where Bohr's atomic theory comes into play. He made a theory, he made a diagram which is still being used today. That means it's still being used today, it's still correct. So in the center we obviously have our protons and our neutrons and the electrons, since they're negatively charged, they're going to be somewhat attracted to the protons, right? So these electrons, they're going to revolve around the nucleus. Why? So because this is obviously negatively charged, and because it's attracted to this, it's going to revolve around it. And fun fact, this model, that Bohr atomic theory, was taken up. The example was taken from the solar system, obviously, because in our solar system we've got the sun, then we've got all our planets moving in an orbit. They are revolving around the sun in an orbit, right? Like for example, this is Earth. As you can see, it's moving around. Very similarly to Bohr's atomic theory, to Bohr's model. They are very identical, as you can see. So this is Earth revolving around the sun, right? This is the sun right here. And you can see this is Mercury, Venus, Earth, and it's revolving around the sun. That's the exact same thing that's happening here. So the nucleus is acting as the sun, and we know what the nucleus is. It has protons and neutrons. And the electrons are acting as the planets. So now I want to draw Bohr's proper atomic model. So first, the nucleus. This is the nucleus. I'm just going to represent it with the positively charged side, obviously. And then we've got the first orbit, the second orbit, and the third orbit. There's the fourth one. So this is the nucleus. I'll just shade it out so it's easier to see. This is the first orbit with 2 electrons, the second orbit, and then the third orbit. So don't look at the electrons and look at the number of electrons, but what exactly are these shells? Well, the first shell is the K shell, the second shell is the L shell, the third one is L. So it goes like this: K, L, M, N, and it continues. So these are the first 4 orbits, right? These are the first 4 orbits which are named, and it goes down the alphabetical order. So K, L, M, N, O, P, Q, R, S, T, U, V, whatever. But then what we can also say is we can take an N value. Now what does this N represent? Which shell is the electron in? Which shell is the electron in? So to represent N, we use numbers. So for example, the first shell is the K shell is the first orbit, L shell is the second orbit, M shell is the third orbit, and N shell is the fourth one, right? So the N value for these just represent which orbit it is. For example, the K1 is the first one, right? So the L value for K, for the K shell would be N is equal to 1. For the L shell, it would be 2. For the M shell, it would be equal to 3, so on. So this is a way to represent the orbits in a numerical value. Obviously, because we've got in an alphabetical order, we can represent it through alphabets as well. But with alphabets, it's not going to help us in calculating stuff. Alphabets don't help us in calculating, right? We need proper values. So that's why we got these numerical values, which is very simple. It just represents which shell. For example, obviously this is the first shell, right? The first shell is nothing but n is equal to 1. Second shell n is equal to 2. So on. So on. So I'll just erase this because we've got, this is very important. So next. Now, because these are all orbits, right? These are all orbits. Let me remove this again. Sorry about that. Won't it also, what would a body with motion have? Would it have some momentum? Obviously, right? Because what is momentum? Momentum, P is equal to mv. P is equal to mv, right? That's it. But, do you think the momentum for this, if we were to calculate the momentum for our electrons, would it just be equal to mv? No, it wouldn't. Because of two situations, because we've got two situations. The electrons are moving in a circle. Hence, it would have some angular momentum, not normal momentum. It would have angular momentum. So it has angular momentum, not normal momentum. So to calculate angular momentum, we have a different formula, which is nothing but mvr, which is angular momentum. So to find angular momentum, it's nothing but P is equal to mvr. So it's just the same formula, but just adding the radius, alright? But now to calculate mvr, now instead of calculating for P, we actually don't need P. We need velocity. Usually we use this formula to find velocity. But then how do we find it, right? Because if momentum is not given, then how do we find it? Well, lucky for us, mvr is equal to nh by 2 pi. Now this formula was derived by Bohr while he discovered it. And how did he calculate this? It's because whenever he took the momentum, because he already knew the momentum, he realized whenever the electron was in the first orbit, I was getting h by 2 pi. Whenever I was in the second orbit, I was getting 2h by 2 pi. So he decided that it would probably be like that. So hence, he made a constant formula, mvr is equal to nh by 2 pi. Now this is a very important formula. H is Planck's constant. So why have we made this a constant? Well, as every single constant, it becomes easier to note down values because H is actually a pretty complicated value and it would be difficult for us to always write it. Ergs into second, or H is also equal to 6.625 into 10 to the power minus 34 joules per second. Now, as you can see, what is erg and what is joule? Joule is obviously the SI unit for energy, but ergs is nothing but an SI unit for energy as well. It's a unit for energy, not an SI unit. But when our value of energy is so small, that's when we take ergs. For example, you can see here, 1 joule is equal to 10 to the power 10 to the power 7 ergs. Can you believe that? Or 10 to the power minus 7 ergs, 10 to the power minus 7 joule is equal to 1 erg. Can you believe that? That's how small the joule value has to be. That's why here we usually take the erg value, because you can see H is such a small value here, 10 to the power minus 27 ergs in itself, but then when we talk about joules, it's 10 to the power minus 34. Imagine how minute that would be. And obviously it would be so minute because we're talking about an electron. Now there are some issues with this theory. Nowadays, we still teach this theory because it's somewhat correct, but it's not 100% correct. Why is that? It's because this only applies for H like species. H like species. Now, what do I mean by H like species? Hydrogen. Hydrogen. Hydrogen is obviously H, which only has one electron. Helium has two electrons, and lithium has three electrons. Now, how am I supposed to make helium similar to hydrogen? By removing one electron from hydrogen, right? From helium, sorry. So if I were to remove one electron from helium, which would make it He plus, that would become one electron in helium. Now similarly for lithium, what would I have to do? I would just remove two electrons and it would become Li2 plus, with only one electron. So the Bohr's atomic theory only implies or only works for H-like species.